Good morning. I have two topics for you. The first one is programming style. This is the part of your program that is ignored by the compiler. And some people think since it's ignored by the compiler, it doesn't matter. You can do anything you want. It's not important. You know, opinion reigns. I'm going to try to persuade you that's not the case, that some styles are significantly better than others for really good reasons. The other topic is your brain, which you know is that big wad of meat that you keep in your skulls. Now you might wonder, what could that possibly have to do with programming? But it turns out there's an unexpected connection. So I'm going to be misrepresenting the work of Nobel Prize-winning psychologist Daniel Kahneman. Nobel gave him the award for economics. He's not an economist, he's a psychologist. But they don't give an award for psychology. He found that one of the fundamental assumptions of economics doesn't hold, which is that any party can be expected to pursue their own best interest. This turns out not to be the case if one of those parties is a human being, because we do not think the way economists think we think. We don't think the way we think we think. And the more you study Kahneman, the more amazed you are that we ever get anything done. So Kahneman came up with a metaphor, a model of two systems that we use to think with. There's system 2, which is the higher level system. It's analytical, it's algorithmic, it's where we do arithmetic and higher reason. It's really smart, but it's also very slow, and it requires a tremendous amount of effort in order to make that work. It's because it's so slow that we invented computers, because System 2 just can't generate the numbers we need fast enough. Then there's System 1. System 1 is very, very fast. It's associative, it's heuristic. It will tend to solve hard problems by substituting the solution of an easier problem. And as a result, it's approximate and sometimes gets things wrong, but it's fast and you cannot turn it off. System 1 is running constantly. Now, we all have a sense that this is true. I mean, you can think of System 2 as being the head and System 1 as being the gut. And we're always saying things like, well, my head tells me this, but my gut tells me that. That's really familiar. What Kahneman found was the surprising connection between the two, which is that System 1 provides the working set, the working assumptions that System 2 uses to do its work. And System 1 is often wrong. So anytime you have a logical system that can have false premises, false inputs, you can get false outputs. And it turns out we do this all the time. So let me give you an analogy from visual processing. Visual processing is the opposite of computer graphics. It's where you take a signal from a camera and analyze all the pixels and try to determine what is in the scene and how are all of those things moving relative to you and each other. This turns out to be a really difficult problem to solve. But we do it. We do it in our heads constantly because we need to be able to do it in order to walk around and not bump into things. There's obvious evolutionary value in having an analytical system in the visual system that works really fast. And the way we do it is by doing the thing that System 1 does. We can't solve the hard problem. So instead we solve simpler problems, which most of the time give us the same result, but sometimes give us incorrect results. And we call those optical illusions. So this is an illusion developed by Edward Adelson of MIT. And here we have a checkerboard with white squares and black squares. And there's a cylinder casting a shadow. And two of the squares are labeled A and B, and those two squares are exactly the same color. If you load this in Photoshop and put the dropper on them, you get exactly the same grayscale value. To demonstrate that, I take a solid colored square and connect them, and in fact, they're the same color. Now, some of you may be seeing a gradient. It's not a gradient, it's a solid color. And if you cover up square B, the gradient may disappear. And if you drop your hand, then the gradient reappears. Your brain is lying to you. And there may be good reasons for why it does that. If a computer system becomes inconsistent, there's a really good chance it's going to fall over. A biological system can't tolerate that. We have to keep going in the face of inconsistency. So we have another system which apparently is looking at what we're thinking constantly, and if something from the inside or from the outside world contradicts it, it will ignore it. So we're very good at ignoring the evidence of our senses and our experience in order to keep ourselves consistent. So it turns out none of this was news to the advertising industry. They've known about this for years and years and years. Kahneman just validates what they've always been doing. They know that they could craft a message specifically for System 1, bypass System 2, and convince us that we desperately need things that we really don't need at all. System 1 can't do arithmetic, so that's why when you go to the market, you'll see a lot of things priced at $199 and nothing priced at $201. Even though there's only 1% difference, it's because System 1 thinks there's a huge amount of difference between those two numbers, when in fact that difference is very small. Now, nobody understood this better than the tobacco industry. Because you think about, how do you sell tobacco to people? You know, what's it do? First, it makes you smell bad. It turns your teeth yellow. Then it makes you sick, and then it kills you. Okay, so how do you sell a product like that? You're not selling it to the head, right? You're selling it to the gut. So this is the machinery that we have in our heads that we use to write computer programs. There was nothing in our evolutionary experience to prepare us for this, but somehow we're doing it anyway. And programs are hard to make. Programs are the most complicated things that humans make. There are more pieces involved in a program that have to all be assembled in such a way that they all work together. There's nothing else that we produce that has so many parts that all have to work with such precision. So early on, as computers started coming online after World War II, it was recognized programming is way too hard. We need to figure out a way to let the computers write the programs for us. And that began the research into artificial intelligence. AI has gone on and done some amazing things. They can play chess now really well. They can play a pretty good game of Jeopardy. But you cannot give a set of requirements and user interviews to a program and say, write a program. That doesn't work. We have no idea how to do that. So as a consequence, we are still writing programs by hand. That's the best we can do, because we cannot describe the process by which we write programs. I can't write down a list of instructions and give it to you, and by following those instructions exactly, you could write programs. We don't know how we do it. We're constantly shifting around as we're working on a problem. We'll look at it top down and bottom up and inside out and macro views, micro views. We're constantly shifting around until eventually we get the right answer, and we cannot describe what that process is. Somehow we all figure it out anyway. So the one tool that we do have is the programming language, because one thing that computers are really good at is translating one formal language into another. And so once we can get something into any kind of a programming language, we can then transform it into other mechanical languages, which eventually will cause some sort of execution. And every generation or so, we manage to raise the level of abstraction in our languages, which allows us to become more productive. And that's the way we make progress in programming. The thing that makes programming so hard is that it requires perfection. A program must be perfect in every aspect, in every detail, for every possible input and every possible state, even inputs and states that were not considered during the design of the program. It has to be perfect over all of that. Because a license we have with the computer is that if the program is not perfect, it has license to do the worst possible thing at the worst possible time. And it's not even its fault. Whose fault is it? Yeah, it's your fault. You're the ones who get the calls. You know, why did you give us a program that's not perfect? What's wrong with you? Now, you would think, given that, we would never release a piece of software until it is perfect. But we can't do that. Perfection is not achievable. And even if it were, we wouldn't recognize it. We have no test that we can give to a program that proves that it's perfect. You can pass a set of tests, but no one is foolish enough to believe that passing the tests means that the thing is perfect. We just don't know. So we can't hold it until it's perfect because we would never finish. We would never know when we were done. So instead, we release it early, knowing that it's got to have problems in it, hoping that we'll discover them before somebody else does. It's crazy, but that's the state of the art. That's the best we have figured out we could do. And we're doing this with the brains of hunters and gatherers. We are hunters and gatherers. There's been no human evolution, at least since the Ice Age. And there was nothing in that experience to have prepared us for writing programs. So it's kind of miraculous that we're able to do this at all. So, so we have this brain that was evolved for a completely different purpose, and we're now using it to write programs. And I think we're making full use of everything we've got. You know, we're using System 2, obviously, because there's so much in programming that's analytical, but there's a lot that we're using System 1 for. So that thing where we take the problem and look at it from every angle, something is shifting us around, taking us to these moments of insight. And I think that's System 1 doing that. So I think programming would be impossible if it were not for System 1. Now, I have absolutely no evidence to support that statement, but my gut tells me it's true, so I believe it. So programming is all about making trade-offs, and making trade-offs is hard because at the time that we have to make decisions, we have incomplete knowledge as to what the criteria for the ultimate solution is going to be. So we make guesses, and we take approximate steps, and somehow, if we get enough of those right, we'll end up with something that's working. And trade-offs require a lot of analysis, but we tend to make most of our trade-offs with System 1 because System 2 can't make those decisions without adequate data, and usually we don't have it. So I'm going to give you some examples of programming style, and the examples are going to be from JavaScript. JavaScript's an interesting language because it contains some of the best parts ever put into a programming language, and it also contains some of the worst parts ever put into a programming language. Now, it turns out every language has good parts and bad parts. There is no perfect language. It's just JavaScript is more extreme in its goodness and its badness. But all of the analysis that we're going to go through could be applied and should be applied to all other languages. JavaScript is not unique in this respect. So because JavaScript has so many bad parts, it really is a dangerous language to work with. It has a lot of edge cases, and those edges can be very sharp and dangerous. So I wrote a program called JSLint, which is written in JavaScript, which reads my programs and tells me when my programs are using the bad parts. And in that way, I'm able to be more defensive in the way that I write, and I write code which is more likely to be closer to perfect and more portable, that'll run in more locations. So it's on the web, it's there for free, you should all be using it. Now, it comes with a warning. JSLint will hurt your feelings. And it's true. I felt it. You know, after I make a change to JSLint, I'll run my old code through it, and it'll go snap. Oh, you know, and I really do understand that it hurts. And I hear from people all the time crying, "Wow, JSLint, you know, doesn't like my program. Can you change it so it stops being mean to me?" And after many years of this, I started to wonder, well, wait a minute, there's no crying in programming. You know, what's going on here? That it's a code quality tool. They put their program intentionally into it for it to tell them how to make it better, and it gives them good advice on how to make it better, and they go, no. So there's something going on here. I think System 1 is involved, because it's an emotional reaction. It's not a rational reaction. So you can get programmers arguing about pieces of style endlessly. It's a completely unproductive activity, but we really seem to enjoy it. So, you know, here's a question. Should you put the curly braces on the left or the right? Turns out there's not a good reason to do one way or the other. It's sort of like driving. In my country, we drive on the right. You guys drive on the left, mostly, from what I've seen. And there's no evidence that says one is better than the other. It's not easier to drive in one system or the other. Accident rates are comparable. You know, there's just no reason to prefer one to the other, but there's a really good reason for everybody being on the same side. So you want to be consistent. And everybody can agree that we should all be consistent, and everyone can agree that everybody in the world should do it the way you do it. But beyond that, there's no agreement because there's not an obvious right answer. Do we put the curly braces on the left or on the right? When Ken Thompson designed the B language, which was his reinterpretation of BCPL, which was the first curly brace language, he put them on the right because it just seemed to make sense for him. And when Dennis Ritchie added Pascal-like types to C, he did the same thing. But there were guys in their lab at Bell Labs who said, no, we want to put them on the left. And I'm sure they had a meeting. And it probably lasted a couple weeks. And at the end of the meeting, Thompson and Ritchie said, leave us out of this. This is a stupid argument. There's not a right answer. We don't care. Do what you want. Leave us alone. Which is a shame, because at that time, Thompson could have said, you know, the compiler says you got to put them on the right, and that's it. End of discussion. Who knows how many man-centuries we would have saved in this pointless, stupid argument about where they go on the left or on the right. So if you have someone who has, in the past, put them on the left, and he goes to work for a shop that puts them on the right, they're going to say, okay, you got to put them on the right now. He's going to start to cry and go, no, I don't want to put them on the left. And you know, system 1 is screaming, this is so wrong. And system 2 goes, that's right, it's wrong. And we'll start trying to rationalize, yeah, why is that? There must be really good reasons. We wouldn't be crying and so upset if there weren't some really important truth here. This is something fundamental and deep. And there's nothing there. There's not a good reason for why one or the other. You just want to be consistent. Except in JavaScript. And in JavaScript, you want to always put them on the right and never on the left. And here's why. Here we've got a return statement that's returning the result of an object literal. This happens a lot in JavaScript. This is one of the good parts. But one of the bad parts in JavaScript is this really stupid thing called automatic semicolon insertion, which sometimes it was intended to allow beginners to not know what the grammar of the language was. So it would attempt to put the curly braces in automatically, and it very often gets it wrong. And this is one of the places where it gets it wrong. So if you put the curly brace on the right, it does exactly the right thing. It makes an object, it returns that object, everything works, everything's good. If you put the curly brace on the left, it will insert a semicolon after the return, and the object literal then gets misunderstood as being a block that, or a block that doesn't do anything. And so there's no warning, no compile time warning, no runtime warning. It's just that your program is going to fail, and possibly not fail here, but fail someplace downstream from this. And so when you go to debug this, you have to go, where's my object? And you might trace it back to the statement, and you're going to stare at that for hours and go, where's my object? Where did it go? You know, it's a huge waste of time, very painful. And it happens if you put the curly braces on the left, and if you put the curly braces on the right, you will never experience this hell. Okay, so you look at it as a trade-off. If I put the curly braces on the right, it just works right. And if I put the curly brace on the left, someday you will experience this. So I'm not saying that every time you put them on the left, it's wrong. It's just if you put them on the left, you're more likely to experience this. And this is a huge waste of time, and you completely avoid that. You just always put them on the right. You look at it as a trade-off. You know, the benefit is obvious. You avoid a lot of pain and suffering. What is the cost? Well, there's no cost. There's no reason for, it's just punctuation. Just put them on the right. There are even programs that'll fix your code and do that for you automatically. That's a good trade-off, at least in this language. So you want to prefer forms that are error-resistant, because we're striving for perfection. We won't reach perfection. We don't even know what perfection means, but it's still something we want to strive for. So we want to avoid forms that are more likely to be imperfect. Another thing that Thompson gave us was the switch statement. It's a multi-way branch, and it's problematic. It's problematic because he modeled his after the Fortran computed goto statement. We learned that the goto is harmful, and it is, and we have removed it from all modern languages, but it still survives in the switch statement. And the hazard is that you can have one case fall through into another case unless you explicitly break the flow of the program. You have to disrupt it, and if you don't, it falls through. So one day early in my experience with JSLint, someone wrote to me and said, you know, there is this hazard with the switch statement, that you got the fall through, and that's bad. And it's a subtle error. It's really difficult to see, but it can really cause disaster in your programs. And I thought about it very deeply, and then I wrote back to him and I said, yeah, maybe, but there's this thing that happens when you get all the cases to line up, they cascade, they flow one into another, and that is really elegant. And this hazard that you're talking about, that hardly ever happens, and there's this elegance that you would lose if you tried to enforce that. So, you know, thinking about it in terms of benefits and costs, I think I'm not going to give a warning on that. Okay, so the next day, the same guy wrote to me, said, I found a bug in JSLint. I said, great. So I throw it in the debugger. Yeah, you know where this is going, right? So I had a case that was falling through. And in that moment, I achieved enlightenment. Because it turns out we're making mistakes all the time. You know, we're dealing with so much stuff, so much complexity. We spend most of our time making mistakes and correcting them. We imagine that we spend most of our time power typing. You know, I'm typing a program, da 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 da. You know, and at the end of the day, we think, yeah, I did a lot of power typing today. It's been a good day. It turns out that's not what we're doing. We're mostly making mistakes and fixing them. And so we'll go into the abyss for a while, and we'll find it, and then we come out, and then there's this little rush of euphoria, like, hooray, I found it. And then we black it out. And so when we look back, we've completely forgotten how much time we spent in the void. All we remember is the time we spent power typing. And because we forget about that experience, we tend to not learn from our mistakes. And so we'll tend to make the same mistakes over and go, oh, did it again, and oh, what was I saying? And we go off. So we're constantly doing that. But on this particular occasion, this was so humiliating. There is no way I could run away from the experience. That I had just given this speech about how this was a really good thing, and then boom, it was the cause of a significant error. You know, how could I have been so wrong? So I, you know, kind of pulled back and look at what was I thinking. So I realized a couple things. One was that elegance I was talking about is worthless. And in fact, in some cases, it's actually negative value because you're adding cruft to your code and forcing things to flow through. You're actually causing a kind of coupling that makes the program more fragile and harder to maintain. If you just replicate a couple statements, that goes away, and it's much more likely that someone else could maintain the code without breaking it. That turns out to be much higher value than this mythical elegance. But the really big mistake I made was I said, that hardly ever happens, which means it happens. This is System 1 talking. System 1 is terrible at math. It gets a lot of things wrong. It will confuse not very much with none, as it did in this case. It will give more weight to most than to all. It's just bad at this stuff. And if you rely on your gut in making decisions about even trivial things like programming style, you can get really messed up, as I did in this case. So a good style can help produce better programs. Style should not be about personal preference or self-expression. It should be about reducing your error rate. It should be about trying to be ever so slightly closer to perfection, about spending less time in the abyss. So we can find some clues to programming style in literary style. The Romans wrote Latin all in uppercase with no word breaks or punctuation. And that worked pretty good for them. It's hard for us to read, And there are potential ambiguities in it. For example, the third line could be read now or DB reeks. You know, but it doesn't. It means the other thing. But there's an ambiguity there, and ambiguities can sometimes cause errors. But generally, they were doing pretty good. Until Constantine established Christianity as the state religion of the Roman Empire. And at this point, it became necessary to make copies of the sacred documents and distribute them all over the world. And the problem was they didn't have originals of any of those documents. All they had were copies of copies of copies, and none of those copies agreed. It turned out every time they made a copy, it mutated. And that was a problem for an institution that was claiming its authority based on the word, and nobody was sure exactly what the word was. So medieval copyists introduced lowercase word breaks and punctuation. And these innovations helped to reduce the error rate. It made it much easier to copy the manuscripts without introducing errors. And unexpectedly, they also made the documents much easier to read. When Gutenberg started printing, he copied those conventions because they had a couple centuries of experience with them, and they worked. And we're still using them. Everything we publish today, all of our writing, everything online, everything on paper, all uses this stuff. We've all been trained since kindergarten to recognize the forms of style, at least as related to English. So if you're an author and you want to demonstrate your creativity, you don't do it by messing with the deep rules of style. You don't take your periods and put them at the beginning of your sentence and not the end because you want to show how creative you are. You know, the critics are not going to say, "What masterful use of punctuation." No, they're going to say, "This clown's illiterate. He needs an editor. He shouldn't be writing books." So you don't want to deviate from the forms of style unless you've got solid evidence that there's a clear benefit for having done that, because we've all had so much education in these conventions. They showed that good use of style can help reduce the occurrence of errors, so that's something that we want to do. There are a number of good style books out there. This is one of my favorites. This was a self-published book by William Strunk. Some of his advice is a little dated because he wrote it 100 years ago, and English has continued to evolve since then. But most of his advice is still relevant and is really, really good. And a number of computer scientists have recognized that and used his book as a model for elements of programming style. It's a very effective source. So programs must communicate clearly to people. It's not good enough to get it through the compiler. Some people think, well, as long as the compiler understands it, that's all that matters. And that's not true. Particularly as programs get larger and more complex, more people are going to be working on it. Sometimes people are working on a project at the end who weren't part of the project at the beginning, going on and on through maintenance. None of that works unless the program clearly communicates to the humans what the program is supposed to do. So we should be using the elements of good composition where applicable in our programs. So anytime there's a convention that seems to work or that maps over, for example, you put a space after a comma, not before the comma, or you don't leave it out, you should do that. And you shouldn't tolerate the argument saying, well, I should be able to write it anyway and the reader can figure it out. We don't accept that for writing, and we shouldn't accept it for programming either. We don't want the readers to be wasting their time trying to get past your faulty technique. We want them to be focusing on what's really going on so that they can be more productive. So some programs require more precision than English literature does, so we'll need additional style rules. For example, we've got braces which are ambiguous because we sometimes use them for mapping and control structures, and sometimes we use them for function declarations and invocations. So we can have a convention like we never have a space between a function name and a left parent, and that makes it easier to identify when something is a function or is defining a function and when it's not. The compiler doesn't require this, but good style does. So one of the good parts in JavaScript is the immediately invocable function expression. This allows us to have a function which we then invoke immediately. So here we've got a function literal, and those parents at the end of it will cause it to be executed right away. This turns out to be really useful for creating modules within JavaScript. So I can create variables within that function which will not escape into the global environment. That turns out to be a really useful thing. Unfortunately, one of the bad parts in JavaScript is that it has function statements and function expressions, and they look exactly the same. And function expressions can be immediately invoked, but function statements can't. So if something is in function position or in statement position, we can't immediately invoke it. So this, as written, will cause a syntax error, which is unfortunate. Now, people figured out that simply by wrapping the function in parentheses, that moves it into expression position, and now you can immediately invoke it. But I think there's a problem with this, that we can do more for the reader. This is sufficient for getting it past the compiler, but this is a slightly confusing construction, and I want the reader to see that what's important here is not the function, so there's no point in wrapping that in parentheses. What's important is the invocation. So the invocation is actually the most important part of this expression. So I want the parentheses to include it too. I don't want the invoking parentheses to be hanging out there like a pair of dog balls. Ladies may want to look away. So my advice is instead we wrap all of that in the parentheses because, again, we want to see the whole thing as a unit. So this is where we start looking at style not just as something to make the program more presentable to the compiler, but making it more presentable to the reader. So I told you about automatic semicolon insertion and how awful it is. This is one of the cases of awfulness. So if the statement before this one, before our function, was not properly terminated with a semicolon, then it will completely misinterpret what's going on here. And it will call y as a function passing the result of the other function as its argument, which is completely wrong. And we don't get a runtime warning, we don't get a compile time warning, it just goes and does the wrong thing. This is another one of the bad parts. So the lesson here is don't depend on automatic semicolon insertion because it is faulty. If you go to the ECMAScript standard, it will show you cases like this of where it fails. It was a well-intended thing, but it was a badly designed thing. And so you don't want to be dependent on it because there are times when it will screw you up. So my advice is put all the semicolons where they're supposed to go. If you have trouble with that, JSLint will help you. It knows where they go. Another thing that JavaScript got wrong was the with statement. This was intended to make it easier to write certain kinds of object expressions, but it's problematic. So here we have in green a with statement which will take object O and do stuff over foo and coda, and it could expand into one of these four statements. Can anyone guess which of the four statements it will expand into? I'm not surprised. It's a trick question. It could expand into any of them. There's no way you can tell reading this program which one it's going to do. In fact, every time that statement executes, it could be a different one. So this is a problem because we're trying to be perfect. And in order to be perfect, we have to understand what the program is intending to do. And if we cannot read the program and figure that out, we've got a problem. So my advice is simply do not use the with statement. By not using the with statement, this class of errors can be avoided. So I'm not saying that every with statement is going to be an error, but every with statement is a problem, and it's unnecessary. So since it is problematic and it's unnecessary, we can simply get rid of it. Now, some people would argue that with is sometimes useful, and so you should use it in the cases where it's useful. But I'm not saying that it isn't useful. I'm saying there's never a case where it isn't confusing, and confusion is the enemy. We want to eliminate as much confusion from our programs. We want it to be obvious what our programs are going to be doing. So whenever a program appears to be doing one thing and actually does another, that's where bugs come from. And if you can't read the program and understand clearly what it's attempting to do, there's probably a potential bug there. So another of the design defects in JavaScript was the double equal operator, which completely fails in the transitivity test. There's actually a strict set of rules which determine these outcomes, but they are complicated and unexpected, and very few people can reliably predict what the result of double equal is going to be. Fortunately, we have a triple equal operator, which is 50% harder to type, but it does do the right thing. It will produce false in all these cases, which is what you want. So my advice is always use triple equal, never use double equal. It turns out you don't need double equal, and you've got the more reliable one, use that instead. So if there's a feature of the language that is sometimes problematic, and if it can be replaced by another feature that is more reliable, then always use the more reliable feature. That way people who are reading your program, if they see a double equal, they can go, okay, this is an error. Or is it? You don't want them to be asking those sorts of questions. You want it to be clear what your program is doing. This is a relatively new feature that was added in ES5. I think this was a mistake, multi-line string literals. This was something that was copied from a number of other languages. I have two problems with it. One is indentation is really important in the formatting of our programs because we have so many nested blocks, nested functions, nested objects. We need the indentation to help us keep track of what is what. And this form requires that the continuation go all the way out to the margin, which breaks indentation, does make programs harder to interpret, and that's a bad thing. But there's a much more serious problem. Here we've got two statements. One of them is correct, and the other is a syntax error. Can anybody spot the error in the second statement? Anyone? I'm sorry? Yeah, there's a space right here. It's obvious once it's pointed out, right? So I want my programs to look correct, and so I don't want to be using forms that are impossible to distinguish from common errors, and this is an error. So avoid forms that are difficult to distinguish from common errors. This is an ambiguity that was in C. It's not in Java, but it is in JavaScript, so it sort of skipped a generation. So we have the first statement, which appears to do what this one does, but actually does what that one does. So if you're reading a program and you see that, you have to wonder, okay, which one? The only thing you're sure of is that the programmer was incompetent. But you don't know which of these. Is it a correct statement or is it a bug? It's really hard to tell. So my advice is figure out which one of these you meant and write that instead. Don't write the thing that's ambiguous. Make your programs look like what they do. Scope is one of the best inventions in the history of programming languages. It came into the mainstream with Algol 60, one of the best language designs we ever saw. Algol gave us block scope, which is great. JavaScript, unfortunately, doesn't have block scope. It only has function scope. Now, it turns out that's okay. Function scope is all you need to write good programs. And so you can write good programs in JavaScript with function scope. The problem is that JavaScript has C syntax, so it looks exactly like languages that do have block scope. And so when programmers come to JavaScript from other languages, they get confused and they assume that the rules of block scope apply, and they don't. And that confusion can cause bugs. So the problem is that JavaScript's var statement does a bizarre thing that you would never expect. The var gets split into two pieces. The declaration part gets pulled out of whatever block it's in and moved to the top of the function, and the initialization part stays where it is. So as a result, you can't declare something inside of a block because it'll always get hoisted out and it becomes global. So if you come to this language from Java or any other block scoped language, you might want to follow the best practice of those languages, which would be that you should declare any variable in the innermost block at the site of first use. That turns out to be exactly the worst advice to give for a language that does not have block scope. You want to declare your variables at the top instead, because otherwise you're going to get confused. So because of this hoisting thing, you should declare all of your variables at the top of the function and declare all of your functions before you call them. Functions do an even weirder hoisting thing, and you want to avoid that confusion as well. I find this is one of the things that really gets people upset more than maybe anything else. Everybody wants to declare their induction variable in the initialization part of the for statement. And this turns out to go badly in JavaScript because that var gets hoisted too. So you might think that it's being scoped to the loop, and it's not. And there are errors that can happen as a consequence of that confusion. So even in that case, you should move the var to the top of the function. So people say, but that's not how you do it in Java. And I say, write in the language you're writing in. When you're writing in Java, then that makes perfect sense. You'd say for int. But in this language, it doesn't. Now, in the next edition, in the 6th edition, we'll probably have a new statement called let. And let is exactly like var, except it will respect block scope. It will not do the hoisting. So in that case, you can declare a variable in a block, and it will not leak outside of the block. And that will be great. So when that happy day comes, my advice will change to stop using var and always use let, and do it in the innermost block at the site of first use, and that'll be great. Unless you have to run on IE6, or IE7, or IE8, or IE9, or IE10. And we don't know what's in IE11 yet, but certainly if you only have to run on IE12 and up, then you'll want to use let. Otherwise, I'm afraid you're going to have to stick with var. So global variables are one of the evil things in programming languages. They're a big reliability hazard. They're a big security hazard. One of the unfortunate things about JavaScript is that it requires the use of global variables. It doesn't have a linker, so it uses global variables as the only linkage mechanism, which is awful. We'll get a partial solution to that in the next edition when we introduce a real macro or a real module. But until then, you have to be really careful with them. So using functions and objects creatively, it is possible to dramatically reduce your use of global variables. So by doing that, you can make your global variables very rare. And I recommend writing them all in uppercase so that they really stand out, that this is a little unit of hazard. And be very careful when you're working with this because it's global and global things can go wrong. JavaScript has a new prefix, which was intended to make the language look more like Java in the way that it constructs objects, but it didn't fool anybody and is really problematic. One of the problems is that if you write a function intended to be a constructor function and your users forget to put the new prefix on it, instead of initializing a new object, it will instead clobber global variables. And there's no compile time warning, there's no runtime warning. This is terrible. This is another of the really bad parts. So in order to defend against that, we have a convention. Use initial caps for naming your constructor functions, and do not use initial caps for any other purpose. And if you can stick to that rule, then we have at least a visual convention for alerting us to the cases where new is missing. Without this convention, it's an error that's impossible to detect. Here's another ambiguous case. This one is unique to JavaScript. So many people will write the top line assuming that it means this one, but it actually means the bottom one, where instead of creating two variables in the current scope, it only creates one, and the other is an implicit global variable, which is horrible. This is a really bad thing. So again, my advice is figure out which one of these you meant and write that instead. Write in a way that clearly communicates your intent. This one's going to be a little controversial. I'll remind you that controversial doesn't mean wrong. Thompson gave us the plus plus operator. It was intended for incrementing pointers in the B language and got copied into C and everything else. Now, since then, we have learned that pointer arithmetic is harmful, and so we don't do it anymore. The last popular language to have pointer arithmetic was C++, a language so bad it was named after this operator. So even though we're not incrementing pointers with it, it continues to exist in our languages for no good reason. It's just there. This operator has been implicated in the buffer overrun craze of the 90s, where it was all of the operating systems were under attack because it was real easy for an attacker to send a payload that was a different size than expected, and code would run off and corrupt memory, and they could seize control of the system. And this operator was implicated in all those attacks, because it turns out that one of the benefits of this operator is that you can take a lot of code and condense it down into one line. And that turns out to be a really bad trade-off, because the value of reducing code to one line is 0. There's no benefit to that. But the cost of complexity is huge, and the code can become incomprehensible. And as a result, it's easier for things like buffer overruns to happen. I find in my own practice, if I'm using this operator, I cannot stop myself. I get this twitch, and I start doing that, and it's stupid, and I know it's stupid, and I can't stop. So ultimately, I had to say, no more. I cannot trust myself to use this anywhere. So I stopped. I'm clean. So now food tastes better. You know, it's great. I can relax. Life is good. And so when I have to add 1 to something, I'll add 1 to it. I'll say plus equal 1. And I don't get the twitch. I'm calm. You know, I'm in control. But I hear from people all the time saying, wait a minute, I should be able to say x plus plus because it means exactly the same thing. I save so much time because instead of going, I only go, I don't have time to. But the thing is, they don't mean exactly the same thing. It means exactly the same thing as that one. So if I see someone writing x plus plus in increment position, I have to wonder, does this clown know the difference between pre-increment and post-increment? And then I have to look at every plus plus in his program and ask, did you get this one right? Did you get this one right? Because this is a really subtle off by 1 bug, because it's only off by 1 for a tiny bit of time. And tracking those down is really painful and really time consuming. And you can avoid all of that if you simply don't use this operator anymore. I was recently reviewing some code and I saw this, plus plus x plus plus x. And you go, okay, what's the story here? It might be a copy-paste error, but I think more likely someone had a off by 1 error and someone else came later and said, oh, he's off by 1, so I'll just fix it. Boom, done. If the original code had said x plus equal 1, then the obvious fix would be to change it to plus equal 2. So it raises a question, why do we need a completely different syntactic form for adding 1 to a variable than every other value? How does that make any sense? Why do we think that's a good idea? I cannot figure that out, but I do know that programmers get extremely passionate about it. If you suggest, maybe you're better off not using plus plus, they get really cranky. You know, you're taking this away from me. It's just, it's a tool that doesn't work right. Anyway, so for no cost by adopting a more rigorous style, many classes of errors can be automatically avoided. And that's a good thing. So here's another one. This is another one that's Thompson's fault. In the original BCPL language, the parens around the condition part were optional, and the braces around the consequence were required. Thompson switched it around, I think, to make it look a little bit more like PL1 or Fortran. And that was a mistake, because it leads to ambiguities like this. It looks like C is called unconditionally. It looks like this one, but it's actually this one. And so that's an error, and we see this happening all the time. And so the easiest fix for this is to always put the curly braces in. It's just 2 characters. It makes your program much more resilient. Anybody can come in after you, and they're much more likely to be able to improve your code without breaking it. That turns out to be a really good trade-off. And yet I hear from people all the time saying, I don't have time, because you have to go, so hard. I don't have time to get it right. But it's easy, it's just 2 characters. So as our processes become more agile, our coding must be more resilient. Code never gets finished anymore. We're constantly rolling it forward. And so if we can put anything in the way that we style the code, which makes it more likely that someone can successfully improve it, that is a really good trade-off. So, who are the bad stylists? Who would get this stuff wrong? So I break them into 4 groups. First are the people who are undereducated. And it turns out on the web we have a lot of these. People who never had any formal training in programming, who've kind of picked it up. And the way they picked it up was by doing view source of really bad code. And so they never got instruction on what good code looks like. And so they've sort of been imprinted by junk. And sadly, that's sort of the way they are now. It's such a sad story, you almost want to cry. Then there are the old school guys, people who come to, say, JavaScript from other languages because that's the way the jobs are going. So I'd much rather be writing Java or C++, a real language, a man's language, But, so okay, I'll write in your JavaScript, but there's no way I'm going to know what I'm doing. As a principle. So you wouldn't make that mistake with any other language, but for some reason people feel really good about not knowing what they're doing when they're working in JavaScript. That's never a good idea in any language. Then there are the thrill seekers who will find out about some bad thing that you can do and just want to show off their mad skills. Like, yeah, I can use all these things and I never make a mistake, because I can handle it. I think guys like that should have to wear helmets when they're coding. And then finally, the exhibitionists. These are by far the most dangerous guys. So they will read the standard, they will read the documents and analyze them and find all the weird edge cases, all the places in the language that don't work the way anybody would expect. And they will harvest those and put them into everything they write and recommend that other people do so too. And you say, and they'll say, it's okay, that was intentional. I know what I'm doing. And I say, no, if you knew what you were doing, you would not be doing that. So programming is the most complicated thing that humans do. And computer programs must be perfect, and humans are not good at perfect. I am a deeply flawed human being. And I find programming to be really hard. It's a struggle. And so I need a disciplined style in order to help me master this stuff that I have chosen to work with. Designing a programming style demands discipline. It's not selecting features because they're liked or pretty or familiar. It's because they help reduce your error rate. You don't want to be reducing your keyboarding because that's not where the time is spent. Where the time is in the abyss. The abyss is this cold, dark, soul-destroying place where we have to go to in order to figure out, your tower of operators has collapsed into a puddle of confusion, and you're looking to the abyss saying, my God, what have I done? And somehow you have to go down in there and find it and bring it all back up again. So I used to think that when I first learned to program, it was a revelation to me. It was amazing. It was like, I can think about things in a way that I've never been able to before. This is so powerful. This is so wonderful. Everybody should learn how to do this. This is great. I don't believe that anymore. I believe that we're able to do this because there's something seriously wrong with us. A normal person can learn to program, but then they're going to have to go into the abyss. They're going to have to debug something, right? And they'll go down there, and they'll come back, and they say, I'm changing majors. I don't know what's wrong with you guys. This is just no fun at all. we're able to do this for a couple of reasons. One is we're optimists. We're among the most optimistic people in the world, that we know that we can go down into the abyss and we will come back up. It's because of that optimism that we can't schedule for crap. But it's what allows us to do this work. And the other thing that happens is we have this brain damage which causes this sort of amnesia that we forget how awful it was down there and how much time we spent down there. So ultimately, if we want to be more efficient, it's not going to be shaving keystrokes. It's going to be by trying to remove as much time from the abyss as possible, to try to stay up here in the land of the living where we can be productive, because nothing happens down there, and we spend way too much time down there. So the JSLint style was driven by the need to automatically detect errors. In the early days, I spent a lot of time on comp.lang.javascript. I don't know if it's even there anymore, is it? Anybody know? I don't know. Anyway, you constantly see people writing, my program doesn't work, can someone tell me what's wrong with it? So I would take it and throw it into JSLint, and sometimes I'd go, yeah, there's the problem, it's right there. And sometimes it couldn't, and I'd go, okay, well, this program's obviously defective, why can't JSLint find it? And sometimes it was because they were using features which would tend to mask errors. So simply by having a feature in there, like using the comma operator, comma masks a whole lot of things that it could have reported, or relying on semicolon insertion. There are a whole lot of things that JSLint can find if it knows that the semicolons are there. So I reluctantly was forced to accept the idea that forms that can hide defects should be considered defects. Even if they're not contributing to a bug at that moment, they have such a higher likelihood of creating bugs in general that we want to keep all of those out of our programs. That's the best hope we have of becoming more perfect. So the approach I ended up with was language subsetting. It's been said only a madman would use all of C++ because there's so much in there and it's so complex. It's also been said only a madman would use C++, but that's for another time. So I'm not suggesting that I'm taking anything away from you, but more I'm liberating you from the stuff that doesn't work, the stuff that's going to trip you up and cause you pain. So when a language designer is inventing a new language, he'll usually look at other languages and features that he admires and try to assemble them maybe in a unique way, and invariably will try to make up some new features of his own. Because if you're going to make a language which is exactly like another language, you're just wasting your time, right? So you want to push the envelope some way, and sometimes those features and those combinations will turn out and do something brilliant, and sometimes it'll be problematic. And if your language is successful and it gets out there and a lot of people use it, you lose the power to correct those mistakes. It's out there. Because the problem with those features isn't that they're useless, it's that they're dangerous. People will always find clever uses for everything. But you want to help them to be more productive and better programmers, and you lose that power. But it turns out you have that power. You have a power that the language designer does not have, that he's lost. When you look at any language, you can look at each of the features and ask, is this more likely to help me write successfully, or is it more likely to trap me? And you can hone a subset of a language which makes you more productive. That turns out to be a really good thing. So there will be bugs. I'm not promising that this kind of reliance on style will make you bug-free. I am saying that you can shave the odds in your favor and spend less time in the abyss, and that's a good thing to do. So good style is good for your gut. Thank you and have a great day.